Hi everybody, so in this video we continue with Chapter 9, Vectors, Lines, and Planes, specifically Section 9.4, Planes. So to define or specify a plane is to identify it in such a way that makes it unique. One way is to set up an equation in a frame that will identify every point that belongs to the plane. There are many ways of specifying a plane. A plane can be defined first, by three non-collinear points, by two intersecting straight lines, to be perpendicular to a certain direction, and at a specific distance from the origin, for example, by being drawn through a given point and perpendicular to a given direction. A direction for our purposes can be defined by a vector. In the case of a plane, the vector determining the direction is perpendicular to the plane and is said to be normal to the plane. So now we're going to talk about equations of a plane. And the third and fourth ways of defining a plane that we saw in the previous slide are appropriate for deriving equations of a plane. So first of all, we're going to look at the Cartesian or scalar equation of a plane. So consider a plane pi. So this is the plane right here, named pi, and a fixed point P, x sub 0, y sub 0, and z sub 0 on that plane. A vector n is equal to ai plus bj plus ck, and this is called the normal vector to the plane, which is perpendicular to that plane. Hence, we have that n, the normal vector, times the vector pm, which would be this one here, has to equal 0, right? Because they are perpendicular. But we know that pm is going to be x this is from m, x minus x sub 0I plus y minus y sub 0j plus z minus z sub 0k. And since n times pm is equal to 0, then we can do their dot product and we should get 0. Then using the scalar product definition, this can be simplified to a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0, and this has to equal 0. And then from here, if we multiply and expand, we are going to get an expression in the form a times x plus b times y plus c times z is equal to d. And notice that this equation is very similar to the equation of a line in the plane, right? For example, ax plus by equals c. So next we have example 9.36, and it says, write an equation for the plane that contains the point 2, negative 3, 5, and has a normal n equals 2i plus j minus 3k. So from the definition, we know that the form of the equation for the plane is going to be, at least the Cartesian form, is going to be a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0, and this should equal 0. So all we have to do is plug in the values for these variables, right? So for a, we have 2, which we get from here, and this times x minus 2. So this is x sub 0 that we get from here. And then b is 1, and then we get y minus 3, so y plus 3, plus c, which is negative 3, so negative 3 times z minus 5. This equals 0. So now all we have to do is expand and rearrange, and we have 2x minus 4 plus y plus 3 minus 3z plus 15 equals 0, and we end up with the equation 2x plus y minus 3z is equal to minus 14. So next we have the vector equation of a plane. we can write the equation of the plane in vector notation. We use the same setup as before. So we have the normal vector n, which we can see here, a fixed point P, which we see here, with a position vector r sub 0. So this would be the position vector for P. And we also have an arbitrary point M with coordinates x, y, z, and with a position vector r, which we can see here. So the equation, in this case the Cartesian equation for the plane, can also be interpreted as the scalar product of n, the normal line, times r minus r sub 0. That is because the vector Pm is equal to r minus r sub 0, as we know. So their dot product must be 0. This must be equal to 0. We use the distributive property of the scalar product, and we get this expression, which then can be summarized into this expression here, which is the form of the vector equation of a plane that passes through a point with position vector r sub 0 and has a normal n. So next we're going to talk about the unit vector equation of a plane. So we have figure 9.41, which shows vector n as drawn from the origin O. We can see that here, along with position vectors r and r sub 0. So the vector equation n dot product or scalar r is equal to n scalar product r sub 0, and this can be investigated further. Now remember that from the definition of scalar product, we have that this is equal to the magnitude of n times the magnitude of r times the cosine of theta 1, this angle over here. But the magnitude r times the cosine of angle theta 1 is going to be the distance OR, so from here to here, which is d in this case, right? So OR is equal to d, which is the distance from the origin to the plane. Now the same thing can be applied to the other position vector r sub 0, and then if we rearrange both equations, we can get the fact that if we divide either side by the magnitude of n, we are going to get the distance from the origin to the plane. So we have these two equations that are equivalent. So the last result gives us the basis for forming a new vector equation of the plane in terms of a unit vector perpendicular to it. Let us call the unit vector normal to the plane lowercase n. So using the results that we just established, we can write this, right? D is equal to n dot product r divided by the magnitude of vector n, and this is equal to n times r sub 0 divided by the magnitude of vector n. And of course, n over the magnitude of n is going to be the unit vector that is normal to the plane. So we end up with this here. Now this equation is very practical when we need to find the distance from the origin to the plane. The distance from the origin to a plane is the scalar product between the unit normal and the position vector of any point on the plane. We will be showing this in following examples. So we continue with example 9.38, and it says, write a vector equation for the plane that contains the point 2, negative 3, 5, and has a normal n equal to 2i plus j minus 3k. So this is the same that we used previously for the Cartesian equation of the plane, but now they want us to find the vector equation. Now remember that that one is in the form of n dot product r is equal to n, the normal, dot product r sub 0. So this is just going to be 2i plus j minus 3k dot product r is equal to 2i plus j minus 3k scalar product or dot product 2i minus 3j plus 5k. And then from here, we write 2i plus j minus 3k dot product r is going to equal 2 times 2 plus 1 times negative 3 plus negative 3 times 5. And then finally, we write it as 2i plus j minus 3k dot product r is going to equal negative 14. So next we have example 9.39, and it says, show that line L with equation R is equal to 2i minus j plus 5k plus k times 3i plus 2j minus 2k is parallel to the plane P, whose equation is R dot product 2i minus 2j plus k is equal to negative 3. So notice that this is another notation, but this is the same as we saw previously. And find the distance between them. Okay, so here in figure 9.42, we have an illustration to the solution for example 9.39. So one way to solve this is to prove that the direction vector for line L is perpendicular to the normal to P. So for line L, we know that the direction vector is this one here. This we know from the definition of the equation of a line. So that means that this vector is the direction vector of line L. So V is equal to 3i plus 2j minus 2k. And then we know that this is the normal to plane P. So that normal would be 2i minus 2j plus k. So if this line and this plane are parallel, then these two vectors should be perpendicular. In other words, their dot product should equal 0. So let's see if that's the case. So we have 3i plus 2j minus 2k dot product 2i minus 2j plus k. And notice that here we're going to get 6 minus 4 minus 2, which is equal to 0. Therefore, line L must be parallel to plane P. Now they want us to find the distance between them. For this, we would need to find the equation for the plane Q containing line L. So let's find an equation for plane Q containing line L. So we use the formula, right? Normal line times or dot product R is equal to normal dot product vector R sub 0. So the normal is normal to both planes, so we can use this one. Notice that this implies that 2i minus 2j plus k dot product R is equal to the dot product between the normal again, so 2i minus 2j plus k dot product the position vector for line L. So that would be 2i minus j plus 5k. So here we're going to get the equation for plane Q that contains line L. And it's going to be 2i minus 2j plus k dot product R is equal to 11. So now all we have to do is find the distance from the origin to P and the distance from the origin to Q. And then we have to add them up. Now, why is that? Because if you look at this, this equals positive 11 and this equals negative 3. So that means that these two planes are opposite to each other across the origin, as you can see here in the drawing. Notice that this is the origin and they are across from each other. So let's erase a little bit here and we're going to find the distance to P and the distance to Q, and then we will add them up. So the distance from the origin to P is going to be, remember the absolute value of the normal dot product R sub 0 divided by the magnitude of n. And here we're going to get 3 over the square root of 2 squared, which would be 4, plus negative 2 squared, which is 4, plus 1 squared, which is 1. And this is just going to be 3 over 3, which is 1. So now we find the distance from the origin to Q. And this distance, again, same thing, right? Normal times r sub 0 divided by the absolute value of the normal, or the magnitude of the normal. In this case, we're going to get 11 over 3. So this implies that the distance between line L and plane P is 14 over 3, which is the sum of this plus this. So next we have example 9.40, and it says, show that the plane with vector equation r dot product 2I minus 2j plus k equals negative 3 contains the line with equation r equals I plus 3j plus k times 3I plus 2j minus 2k. Now from the previous section, I don't know if you recall, but normally we would use a v here for the scalar instead of a k. So don't confuse this k with this k and this k. They're totally different. Okay, so there's several ways to do this. One way is to pick a point on this line. We could say that this is a point on the line, right? 1, 3, 1 is on line R. And that means that if we do the scalar product with the normal here, 2I minus 2j plus k, we should also get negative 3. So let's see if that is the case. So this would be 1 times 2 plus 3 times negative 2 plus 1 times 1. And then obviously this is going to be 2 minus 6 minus 1, plus 1, excuse me, which is equal to negative 3. Another way is giving a value to v. So let's say v equals 1. Then we would have equation r is equal to I plus 3j plus k plus 3I plus 2j minus 2k. And then here we get 4I plus 5j minus k, which would be a position vector for a point on line R. So then the dot product between this and the normal should also equal negative 3. So we'll see if that is the case. So we go 4I plus 5j minus k dot product 2I minus 2j plus k is going to equal 8 minus 10 minus 1, and this also equals negative 3. Okay, so now we have example 9.41, and it says find the vector equation of the line through 1, 2, 3 that is perpendicular to the plane with vector equation r dot product 2I minus 2j plus k equals negative 3, and find their point of intersection. So this vector equation is perpendicular to the plane. That means that it has to be parallel to the normal, which is right here. So we can write a vector equation for the line in the form r equals 1, 2, 3, which would be our starting point, plus t, which is the scalar, times the direction vector, which in this case would be the normal of the plane, right? So 2, negative 2, and 1. Now they want us to find the intersection between the line and the plane. So we would need to find a position vector on R, and the dot product of that times the normal should equal negative 3. 1 plus 2t, 2 minus 2t, and 3 plus t, right? Dot product 2, negative 2, 1 should give us negative 3, right? We get this from here. So that means that we would get an equation in terms of t here, which would be the following. It would be, remember this is the dot product, right? So it would be 2 plus 4t minus 4 plus 4t plus 3 plus t has to equal negative 3. So now if we add similar terms, we're going to get 1 plus 9t is equal to negative 3. So 9t is equal to negative 4. So t is minus 4 over 9. So that means that the point of intersection would have to be in the form 1 plus 2 times negative 4/9, comma, 2 minus 2 times negative 4/9, comma, 3 plus negative 4/9. And then from here, we're going to get that the point of intersection is 1/9, 26/9, comma, 23/9. So now we're going to take a look at the parametric form for the equation of a plane. So if you look at figure 9.43, it shows that it is always possible to construct a parallelogram whose diagonal is W and whose sides are the non-parallel vectors u and v, or their multiples. So in other words, three coplanar vectors u, v, and w are given. If u and v are not parallel, very important, then w can always be expressed as a linear combination of u and v. It is always possible to find two scalars s and t such that w is equal to s times u plus t times v, as you can see here. So this would be s times u, and this would be t times v, and obviously their sum would equal w. Now take a look at figure 9.44 and consider the plane that is parallel to vectors u and v and contains the point A, whose position vector is r sub 0. The two vectors determine the direction of the plane, and A fixes it in space. So if M is any point on this plane, then according to the previous theorem, vector AM is equal to SU plus TV, where S and T are scalars. If R is the position vector of M, as we can see here, then R is equal to R sub 0 plus vector AM. In other words, it is equal to R sub 0 plus S times U plus T times V. Thus, any equation in this form, where S and T are independent scalars, represents the equation of a plane parallel to U and V that contains the point with position vector R sub 0. Now, it is important to note that this equation is not unique. This is because we can start at any other fixed point on the plane other than A, and we can choose any number of intersecting vectors on the plane other than u and v. The parametric form of the equation of the plane is seldom needed or used. So now let's take a look at example 9.42, and it says find an equation of the plane with normal q equals 2i minus 3j plus k that contains the point 2, 1, 1, and use all forms you have learned. Okay, so I'll leave the Cartesian and vectorial forms to you as an exercise, and I'll do the parametric. So let's remember that the parametric form of the equation of a plane is going to be r equals r sub 0 plus a scalar s times a vector u plus a scalar t times a vector v. Now vector u and vector v have to be parallel to the plane. So that means that they need to be perpendicular to the normal. So the normal, which is 2, negative 3, and 1, has to be perpendicular to u and v. So let's just take 1, 1, z, which is just a random vector that would have to be perpendicular to the normal. So if they're perpendicular, it means that 2 minus 3 plus z should equal 0. Therefore, z would have to equal 1. Let's find another one for v. Let's take 1, 0, z. So because this is perpendicular to the normal, we would have that 2 plus z should equal 0. Therefore, z is equal to -2. So then the parametric equation of the plane is going to be r equals r sub 0, which is going to be the position vector for point A. So that's going to be 2, 1, 1 plus s, a scalar, times the first vector that we found for u, which is 1, 1, 1, plus the scalar t times vector v, which we found was 1, 0, -2. So notice that the vectors u and v are arbitrary, so that means that there's an infinite amount of parametric equations that are possible for this plane. So next we're going to talk about the distance between a point and a plane. So the distance between a point P, x sub 0, y sub 0, z sub 0, and a plane with equation, I should say Cartesian equation, ax plus by plus cz equals d, is given by d equals the absolute value of ax sub 0 plus by sub 0 plus cz sub 0 minus d over the square root of a squared plus b squared plus c squared. So this is very similar to the formula of the distance between a point and a line. Now the proof is here. I leave it to you as an exercise to study the proof. So we continue with example 9.45, and it says, find the distance between two parallel planes, x plus 2y minus 2z equals 3, and 2x plus 4y minus 4z equals 7. So we don't have a formula for the distance between two parallel planes, but we can find an arbitrary point on this plane. And since all points on this plane are equidistant to this other plane, then we could just find the distance between the planes by finding the distance between said point and the second plane. So notice that we can find an arbitrary point in the form 1, 1z on this first plane. So we would have that 1 plus 2 minus 2z is equal to 3. Therefore, z would equal 0. So that means that we have the point 1, 1, 0 on the first plane. Therefore, the distance we can find using the distance formula. Remember that distance formula is equal to absolute value of a x sub 0 plus b y sub 0 plus c z sub 0 minus d over the square root of a squared plus b squared plus c squared. So applying this formula, we substitute in here, and we're going to get that the distance is equal to the absolute value of 2 times 1 plus 4 times 1 minus 4 times 0 minus 7, which is d. And this over the square root of 2 squared, which is 4, plus 4 squared, which is 16, plus -4 squared, which is 16. And if you do the math, you're going to get 1 over 6. So we continue with example 9.46, and it says, find the distance between two skew straight lines. Line 1 is r equals 1, 5, -1, plus lambda 4, -4, 5. Now this is just a scalar, of course. And then for line 2, we have equation r equals 2, 4, 5 plus mu, the scalar, times 8, -3, and 1. So in order to solve this, we need to find two planes that are parallel to each other and contain these two lines. Now, in order for the planes to be parallel, they must be perpendicular to the same vector cross product of the direction vectors. So if we grab direction vector 1 and do the cross product with direction vector 2, we should get a vector that is perpendicular to both vectors, right? So remember that this is going to be I, j, k, and then we have the first direction vector, which is 4, -4, and 5, and then the other one is 8, -3, and 1. So if we do the cross product of this, we're going to get a line that is normal to both of the planes that contain the lines in the problem. So this is going to be 11I plus 36J plus 20K. Okay, so if we consider the point 2, 4, 5, which lies on line 2, so this is on line 2, as we can see here, then we can find an equation to the plane that contains that point. Remember that it's in the form n times r, well, that's dot product, and this is equal to n times r sub 0. So the normal is the one we just found, right? So 11, 36, and 20 times r, which is just x, y, z, should equal the dot product between the normal, 11, 36, and 20, and 2, 4, and 5, which is this right here, r sub 0 for line 2. So from here, we're going to get 11x plus 36y plus 20z equals 266. So the distance between the point 1, 5, negative 1, which is on line 1, as we can see here, and the plane that we just found is going to be d equals the absolute value of 11 times 1 plus 36 times 5 plus 20 times negative 1 minus 266, which is d. And this over the square root of 11 squared plus 36 squared plus 20 squared. And if you do the math here, you're going to get 95 over the square root of 1,817. So now we're going to take a look at the angle between two planes. So the angle between two planes is defined as the acute angle between them, as you can see here in figure 9.47. Consider two planes P and Q with unit normals n1 and n2 respectively. Their vector equations are of the form r dot n1 equals d1 and r dot n2 equals d2. The angle between the planes is equal to the angle between the normal units n1 and n2, or the normals capitalized N1 and capitalized N2, and hence we reach this formula, which is just the formula for the angle between two lines. So we continue with example 9.47, and it says find the angle between the planes with equations 2x minus 3y plus 5 equals 0, and 3x plus y minus z equals 4. So we would need the equations of the normals. That's pretty easy. That's just going to be for the first one, 2i minus 3j, and there's no z. And for the other one, we're going to get 3i plus j minus k. So the cosine of the angle theta between them is going to be equal to the dot product between the normals. So that's going to be 2i minus 3j dot 3i plus j minus k, this divided by the magnitude of the first vector, which is going to be square root of 13, times the magnitude of the next vector, which is going to be the square root of 11. So if we do the math here, this is going to give us 3 over the square root of 33. Therefore, the angle theta is going to equal the inverse cosine of 3 over the square root of 33. So we continue with the angle between a line and a plane. The angle between a line and a plane is defined as the angle theta formed by the line and its projection on the plane. We can see that on figure 9.48. consider the line L with equation R equals R sub 0 plus lambda times A. So this line R would be here. And the plane with equation R dot N equals D. The acute angle phi between N, the normal to the plane, and the line L can be found by using law of cosines. So cosine of phi is equal to the absolute value of A dot N divided by the magnitude of A times the magnitude of N. Now notice that this is equal to the sine of theta. So next we have example 9.48, and it says find the angle between the line with equations x minus 1 over 2 equals y minus 2 over 3, which equals z over 2, and the plane with equation 2x minus y minus z equals 7. So here we need the direction of the line, and this is given by a equals 2, 3, 2. Remember that the direction vector in the case of parametric equations of the line is going to be the denominators. And then the normal to the plane, to this plane, is going to be n equals 2, negative 1, negative 1. So that means that the sine of the angle theta is going to equal the absolute value of the dot product of 2, 3, and 2. So this is A. And 2, negative 1, negative 1 over the magnitude of these vectors. So this is going to be square root of 17 times square root of 6. So here we're going to get 1 over the square root of 102. So that means that theta is equal to the inverse sine of 1 over square root of 102. So now let's take a look at the line of intersection of two planes. So unless two planes are parallel, they will intersect along a straight line. Consider two planes P and Q that have L as their line of intersection. Also let the planes have the vector equations r dot n1 equals d1 and r dot n2 equals d2. Since line L lies in plane P, then N1, the normal to this plane, must be perpendicular to it. This is also true for N2. Therefore, the direction of line L is perpendicular to both N1 and N2. So to find the line of intersection, we can use two methods. First method, cross product of the unit normals N1 and N2 as the direction of L and a specific point on the line. And 2, the fact that all points on L must satisfy the equations of both planes. In other words, we solve a system of equations. So now we do example 9.49, which will be the last one on this video. And it says, let planes P and Q have the equations r dot I plus j minus 3k equals 6 and r dot 2i minus j plus k equals 4. Find the line of intersection using the two methods. So the first method implies doing the cross product of these normals. So let's do that first. We're going to get that I plus j minus 3k cross product 2i minus j plus k is going to give us 2i plus 7j plus 3k. Then we need to find a point on the line of intersection. So we use the fact that the line must satisfy both equations. So that means that the point must be on both of these planes. So let's call an arbitrary point 0, y, z. So we make x 0 out of convenience. So this dot I plus j minus 3k should equal 6. And then in the other case, the same point 0, y, z dot 2i minus j plus k should equal 4. So from here, we're going to get two equations. Y minus 3z equals 6, and minus y plus z equals 4. So we solve a system of equations here, and we're going to find that z is equal to -5 and y is equal to -9. So then we can write the equation of the line in vectorial form. We can say that it is r equals 0, -9, -5, which is a point common to both planes, plus t, which is a scalar, times the normal that we found, right? So 2, 7, 3. Then for the second method, we can just solve a system of equations using the Cartesian equations of the planes. So the first one would be x plus y minus 3z is equal to 6. And the second one would be 2x minus y plus z is equal to 4. So notice that we can cancel out y if we add these. So we would get 3x minus 2z is equal to 10. And then if we rearrange this, we're going to get that z is equal to -5 plus 3/2 x. So if we plug z into this first equation, or you substitute here for z, we're going to get that y is equal to -9 plus 7/2 x. So notice that in these two solutions, x is a parameter. But for the sake of convenience, let's just say that x is equal to 2 lambda. Why is that? Because if we substitute this by 2 lambda, we're going to get rid of these denominators. And we will have a set of parametric equations that represent the line of intersection. So notice that y is going to equal 7 lambda minus 9, and z is going to equal 3 lambda minus 5.